So let's begin with Newton's second law. And let's write it in the following way. Mass times acceleration. So we're going to take the position vector r and evaluate two derivatives of the position vector in time. That's the acceleration. And that's equal to the force. And let's say that the force is the force of gravity. So we're considering an object of mass m. And given that we haven't put an index on it, let's put an index on another object. So we'll consider an object of mass m and an object of mass m. We'll put the index on the other object. We'll call it mb. And r is the vector. From here to there. Well, we could, yes, it's the vector from there to there. The origin of our coordinate system could be anywhere. It doesn't have to be there. We could have the origin over here, and then that would be the difference of these two vectors, R2 and R1, say. But let's just leave it like that. So let's think of the universal force of gravity, so that our equation becomes gmb over r squared, which is just the distance squared. So that's a scalar times r hat, and r hat is just a unit vector pointing that way. Like that. Okay, so let's look at the acceleration term. So we have a two-body system, and we're looking at the acceleration. On this one, we're just dividing by this mass, and so we end up with g and b over r squared r hat. We could write this as g and b r vector over r cubed, because r hat is just r over r. It's r vector over r, the magnitude. Okay, so what follows from this? Well, let's write this as, let's take this a vector product, r times the acceleration, and that must be gmb over r cubed, r hat cross r hat, and of course these are in the same direction, and therefore this must be 0. So it follows from this that if I take the derivative in time of r cross dr by dt, because this thing is nothing more than this. And so you can see that we apply this to the first term, we get dr by dt, cross dr by dt, that's 0. And then we have r cross second derivative of r and t, so this is equal to that. D by dt of this is 0, and so it follows that r, so what follows from this is that r cross dr by dt is some vector, usually it's indicated as h, some vector h that does not depend on time, right, because of this relationship. Okay, so we can conclude that the object of mass m moves in a plane such that the vector position the position and the velocity, dr by dt, or maybe we can write it as r dot, are in that plane. That's a little strange the way we wrote this. But the conclusion here is that position and velocity are always in the same plane.